Hello there, Mr. Sutton here, bringing you the AB Calculus 6-7 Extra Practice number 2 solutions on total distance. On this calculator-based problem, we have a particle moving along the x-axis with a velocity given by this v of t function here, and we're told at time 0, our initial position for the particle is x equals 7. First task is to find the acceleration of our particle at time 5.1. Well, acceleration is just the derivative of velocity, so we basically just need v prime of 5.1. And since I've already defined, or they've already defined for me the v function, this is really all I have to show before calculating the derivative on my calculator, just using the nderiv function. So let's go ahead and do that now. So the first thing I've done is store my v function as y1 in my y equals, and then let me quit out of there and do math 8, put a little x down there for the dx, and then for the function, let me do alpha trace y1, and then I'm just plugging in 5.1, and that's going to come out to about 6.492, and there was no units on this one, so that is our acceleration. For this problem, they want all t values on the interval from 0 to 2, for which the speed of the particle is 1. So first thing we need to do is figure out a way to define speed. Speed is the absolute value of velocity, so I'm going to define speed as this speed equals absolute value v of t, and I'm going to set that equal to 1 on my calculator, and then I'm just going to find where those intersect. So let me go ahead and do that now. So to do this on the calculator, I have to create two new functions in my y equals, one for the absolute value of velocity, one for just the horizontal line y equals 1. So let me do absolute value of velocity first. So let me do alpha window to pull up this little submenu, and the first option there is abs, absolute value. And now my velocity is stored as y1, so I'm just going to do alpha trace and just insert y1 into there, so I don't have to rewrite all of that craziness all over again. So that's absolute value of velocity. Down here, let me just put 1 for that horizontal line. And because I don't want to graph the original velocity function, let me unselect that by pressing enter on the equals here. Now I have to get my window straight, so let me go to window. We're going from 0 to 2, and then let me do zoom 0, zoom fit, and that should give me the perfect window on the intersection of my speed and the value 1. So there's my speed that I'm graphing out right now, and here's the horizontal line 1, and all I have to do is figure out where these cross. So let me go to second trace, option 5 for intersect, and then let me just, where's my spider? There he is. Let me just arrow closer to the first intersection, press enter 1, 2, 3 times, and that's about 0.772. So there's the picture. There's my first intersection, and let me just go back here and get the next intersection. So second trace, option 5, and go over to the other crossing point, and enter, 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 comes out to about 1.401 if I round it off to 3 decimals. On this part of the problem, they want me to find the position of my particle at time 4, and then figure out if it's moving toward or away from the origin at that time. So let's start with the position. That'll actually help us answer the second question anyway. So my position at time 4, which I will just denote as x of 4, that's going to equal my initial position at time 0, which was 7, plus, well, I need my total change in position from time 0 to time 4, so that's going to be the integral from 0 to 4 of my velocity, vt dt. And now I can just plug that in my calculator. So here's what that looks like on my calculator. I have 7 plus integral from 0 to 4 of y1 dx, because y1 is where I stored my velocity function, and that comes out to approximately 6.712. Now the next question is the particle moving toward or away from the origin? Well, we need to answer 2 questions in order to answer that question. First off, am I on the left or right side of the origin? And this is going along the x-axis, so it's a left versus right kind of situation. Now I see here that since my position at time 4 is this number, which is positive, I'm on the right side of the origin. Okay, now the next question is, am I moving left or right? And that's going to determine whether I'm moving toward the origin or away from it. So the left versus right deal, that's all about the sign of the velocity at time 4. So I need to find v of 4 at this point. So here I am back on the calculator to do that, and I just need to plug it in. I just need to plug 4 into my y1. So let me do alpha trace y1, parentheses 4, and then enter. So my velocity at time 4 is this number, which is a positive. Let me just make that into a decimal, because that's just weird to look at. Okay, so about 1.213, which again is positive. So I am to the right of the origin, and I'm also moving right based on this velocity. The sign of velocity and position agree. So this is telling me that I have to be moving away from the origin if I'm on the right and moving more right. For this last part of the problem, we're asking during the interval from 0 to 4 if our particle returns to its initial position. So we're basically asking, do we get an x value of 7 back somewhere between 0 and 4? Okay, so if we're trying to guarantee a certain output value for a function, then we have to use the intermediate value theorem. And to use that theorem, we have to first establish continuity for the function that we're trying to guarantee this for. So we're trying to guarantee that the x function returns 7, somewhere between time 0 and time 4. So I have to show x is continuous. Well, the only guidelines I have here are the derivative of x, which is velocity, v. And velocity, if you're plugging in numbers between 0 and 4, this function here is never going to have 0 in the denominator. I mean, the smallest thing we're plugging in is 0 itself. That would give you a denominator of 3, and everything else is going to be positive numbers, which is not going to zero out the denominator. So we can show pretty quickly that velocity, which is the same as x prime of t, is continuous. This means that x itself is differentiable, and that means that x itself is continuous on the interval from 0 to 4. So this establishes kind of the preconditions for intermediate value theorem. So that guarantees that whatever the starting and ending x values we get back on this interval, that we're hitting all of the output values in between those starting and ending values. So now we just need to figure out the starting and ending values. However, this is a little bit of a twist on this problem. Normally, with intermediate value theorem, we would just plug in the two endpoints, 0 and 4, look at the output values and show that the number that we're looking for falls between those output values. But we can't really do that on this one. The trouble is that the output value we're looking for, namely 7, is exactly what we're going to get if we plug 0 into the x function. So the intermediate value theorem doesn't really prove anything if the output value you're looking for matches one of the endpoint output values. So what I'm going to do to kind of work around this problem is I'm going to pick a starting value that's a little bit more than 0, like 1. If I can show at least that I'm guaranteed to get x equals 7 on the interval from time 1 to time 4, then that'll prove this larger question of 0 to 4. So let me start by doing x of 1, and that's going to be my starting value of 7 plus the integral from 0 to 1 of v of t dt. And now let me do that on the calculator. So recall that I stored my velocity function as y1 in my y equals. So I'm doing 7 plus the integral from 0 to 1 of that dx. Comes out to 9.404 and some change. Now I'm going to also test out x of 4, which is going to be 7 plus the integral from 0 to 4 of v of t dt. And just going back on the calculator, once I've already done this for x of 1, this is pretty quick to do for 4. I'm just going to arrow up and yank my input from before. And then I'm just going to replace this 1 here with a 4 in the upper limit of integration. Press enter. And that gives me the x value back of 6.712. Okay, so the output value we wanted to guarantee we were going to get was 7. 7 is between these two numbers, so I'm going to just write x of 4 less than 7 less than x of 1. Since our beginning and ending output values are sandwiching the value we were looking for, the IVT guarantees that our particle is going to return to x equals 7, our initial position, somewhere on the interval from 1 to 4, which also counts for somewhere on the interval from 0 to 4. For this no calculator free response problem, we have Joanna jogging along a straight path between time 0 and 4, and times measured in minutes here, or 0 and 40, I should say, 40 minutes. 4 would be a very short jog. Anyway, we've got a table of Joanna's velocity at different points in this jog. And for the first part of the problem, they want us to use the data in the table to estimate v prime of 16, which is basically the instantaneous acceleration of Joanna at time 16. So if I'm trying to approximate an instantaneous rate of change, and all I have are table values, the best I can really do is to find the average rate of change over an interval that contains the input value they're asking about. So basically, I'm going to find AROC for v on an interval that contains 16. Probably the best interval to use would be 12 to 20. That's the smallest interval in which 16 falls. So I'm going to do AROC from 12 to 20. So I'm going to say v prime of 16 is approximately equal to v of 20 minus v of 12 over 20 minus 12. So just plugging in some real numbers here, that's 240 minus 200 over 20 minus 12, which is 8, I guess we could simplify that to. So you actually don't need to go any further than this other than putting units on the end, but I'm just going to take it out here to the final conclusion. So we've got 40 over 8, which is going to be 5, and that's going to be 5, let's see, we had meters per minute for velocity divided by minutes for time. So that's going to be meters per minute squared, 5 meters per minute squared. For this part of the problem, they want us to, using correct units, explain the meaning of integral from 0 to 40 of absolute value of v of t dt in the context of the problem. So let's do that first, and then we'll answer the rest of this. So this integral here is basically, since we're taking the absolute value of velocity and integrating it, forcing basically everything to come out positive and pretty much ignore direction changes, this is giving us the total distance that Joanna jogs, and that distance is going to be in meters over the interval from 0 to 40 minutes. So every piece of this is important, the total distance part, the units, and also you have to have the time element mentioned in here to get full credit on this problem. If you didn't mention 0 to 40, then the total distance Joanna jogs over what interval? Like from 0 to 2,000 minutes? I mean, who knows? We got to be specific. Now the next part of the problem is to approximate that integral using a right-Riemann sum with 4 subintervals indicated by the table. So this is kind of like your normal Riemann sum sort of problem with a little bit of a twist, because they didn't give you the absolute value of v up here. They just gave you plain old v. So if you do encounter any negatives along the way, you are going to have to convert them to positives in order to actually find the value they asked about here. So let's start this off. I'm going to say that this integral is approximately equal to the following. I'm making very clear to people that this is an approximation, not the exact answer. So I'm going to have a bunch of base times height rectangle areas. For my first rectangle, going from the interval from 0 to 12, I have a base of 12. And then I'm going to, since it's a right Riemann sum, I'm going to use the right height between these two options for the height of the rectangle. So I have 12 times a height of 200. For the next rectangle, from 12 to 20, that's a base of 8 times a height of 240. For our next rectangle, we have the interval from 20 to 24. That's a base of 4 times a height of, now before you write negative 220, remember this is absolute value of velocity. So this is going to be 4 times positive 220. And then finally, our last interval from 24 to 40, that's a base of 16 times my height of 150. So you could stick units on the end of this and call it a day and not simplify it, and that would be perfectly fine on the AP exam. I'm going to simplify it, but if this were the real exam, I probably wouldn't do this unless I really needed the answer for something else. So going from left to right, this is going to be 2,400 plus, well, let's see here. This is like 8 times 200 plus 8 times 40. 8 times 200 is 1,600. 8 times 40 is 320, so that's 1,920. For this next one, this is going to be 880. And this last one, well, I don't know 16 times 15, but I do know 4 times 15. 4 times 150 would be 600. 4 times that would be 2,400. So just using a little creative mental math here. And then adding all of this up, well, let's see here, 2,400 and 2,400, that's pretty easy. That's 4,800. And 1920 and 880, that's going to be, let's see here, 2,800. So I have 2,800 and 4,800. That's a grand total of 7,600 meters. For this part of the problem, we have Bob riding his bike on the same path as Joanna. Hopefully they don't hit each other. Between times 0 and 10, Bob's velocity is modeled by this b of t function. And let's see here. We want to know Bob's acceleration. We want Bob's acceleration at time 5. All right, well, acceleration in general is derivative of velocity. So we can say a of t, I'm just naming my acceleration function, is going to be equal to b prime of t. Let me actually find what b prime of t looks like, because it's a no calculator question, so I need to know this to plug 5 into it. Using my power rule, this is going to be 3t squared minus 12t. So plugging 5 into all of that, we're going to have 3 times 25, which is 75, minus, let's see, this is going to be 60. 75 minus 60 gives me 15, and got to nail the units here. Since this is acceleration, this is going to be meters per minute squared. For this last part of the problem, we want to know Bob's average velocity, and this was the Bob from part C. So just recall that Bob's velocity function in part C was given by this cubic function here. So we want to know the average velocity now on the interval from 0 to 10. We're going to set this up like just any other average value problem. We're going to do 1 over the interval length, so in this case 1 over 10 minus 0, and this will be average velocity here, times the integral from 0 to 10 of whatever we're trying to average, which in this case is the b of t function. So I'll just write the whole thing out in there. T cubed minus 6t squared plus 300, all of that with a dt at the end. So because I don't have a calculator, I'm going to have to do this by hand using my fundamental theorem. So I've got a 1 over 10 out in front of everything. And next to that, I'm going to have a little evaluation box with my antiderivative. So going from left to right with the reverse power rule, this first one bumps up to a 4. Dividing by that, I have t to the 4th over 4, or 1/4 t to the 4, however you want to write it. And then this next one bumps up to an exponent of 3. Dividing by that, that's going to be negative 2t cubed. And then finally, using my reverse line rule, this is plus 300t. All of this evaluated from 0 to 10. So I've got 1/10, and then I've got all of this stuff with 10 plugged in, minus all of this stuff with 0 plugged in. And all of that's in a huge parentheses with a 1/10 on the outside. So this looks pretty nasty, and actually, if this were the real AP exam, you could stick units on the end. It's average velocity, so it's going to just be meters per minute like normal velocity. You could stick units on the end here. Since it's all constants, you would actually be done. But if you really wanted to simplify this and risk it, here's how you could go about it. So this whole bracket over here, everything is getting multiplied by 0, so this whole second bracket is just gone. So we'll just focus on this first bracket. We're going to have 1/10 times, and now this first thing here, you've got 10,000 divided by 4, which is 2,500. Next, this is 2 times 1,000, so this is minus 2,000, which that'll be pretty easy to deal with. And this last one's going to be plus 3,000. So inside, let's see here, 2,500 minus 2,000 is 500, plus 3,000 is 3,500, and dividing that by 10, we just get 350. Again, that's going to be meters per minute. There we go, because it's meters per minute. Yep, meters per second would be really fast. I don't think Bob's that fast.